So this step 4 says that we are doing a deep dive into the services now. Okay, first of all, let's. So my assumption is that yes, you have gone through the gone through the prerequisites, and you know that what is an inverted index, how does it work, right? So I'll not go into the details. I'll talk about it at a very shallow level first. So what is indexing in this context? So so we create separate inverted index for all the queryable metadata fields, right? So like service, trace ID, datetime, etc. And each word in the message body. So what does that mean? So if you remember about the inverted index, right? If you have seen the prerequisites, so in that we take example of Shakespeare, all the plays written by Shakespeare, right? So in that, let's say there is some word, I don't remember what complicated words are there in that, but let's take only dummy example, right? So let's say there is a word one. Actually, this is how the line is written. Okay, okay, yeah. Let's take this simple only. Right? What's in a name? I'll add some funny thing here. What's in a name of a software service? Let's imagine that Shakespeare wrote this in one of his plays. So what we do that we actually break down these, and yeah, and this is in a document one, right? Then there is another document one means, let's say this is his one of the play, let's say Hamlet, right? Now there is another document two. Let's say there is Romeo and Juliet play. In that there is a line written that software engineers are funny creatures, right? Let's say this is written. Now somebody wants to find out that word software appears in which of the plays from Shakespeare, right? So how do we do that? So we take each and every word and we create a reverse index, right? So we take word what and we write that it is in document one. If you remember, these are just adjacency lists. Then we have the next word name. So it is also in doc one. We disregard these kind of filler words, right? In a, these kind of a, these are not important. Then we take word software. It is also in doc one. And then word service is also there, which is also in doc one. So we have analyzed the complete Hamlet play. Now we will analyze Romeo and Juliet. So it says software. Okay, so doc one. So we already have entry for software, right? So we will just append doc to here. Then there's a new word engineers. So that will be in doc to. Then funny and creature, they will also come here, right? Now if somebody asked that, okay, in which of the documents, in which of the plays word software appears, so we go and check that, okay, so so this is like a hash map, right? So we know that, okay, so we go and check for the entry software. We know that doc1 and doc2 both are there, right? So this is basically an inverted index. Now, in our context of the log search, what we are doing is that for all the queryable metadata fields like service, trace ID, date, time, we will create this index. And for each word also, we will create this index. Let me see if I have example. Hmm. So let's say our log message was transformed into a JSON document like this, right? Now this JSON document has to be indexed. It has to be indexed by so indexed means for timestamp we will have some kind of inverted index. For this service also we will have some kind of inverted index. Then each and every word in the body, right? That error 403, user ID, this hacker 123, authorized, these will be, for them also inverted index will be updated. Okay, so this is the process of creating inverted index and how we are doing it in the context of log search. Okay, so for inverted index and this kind of scenario where we have to search through the text, we generally have off the shelf solution called Elasticsearch. So this Elasticsearch internally they have inverted index under the hood. So but the generally the Elasticsearch, when the data requirement is huge, at that time this Elasticsearch system starts to deteriorate in performance, and managing Elasticsearch becomes a very complicated problem. Now during the interview setup, even if you don't know about this thing, right, that Elasticsearch is is if it's not scalable to a very high number, it's still as an interviewer, I want to know that can you design your own Elasticsearch, because that's the whole purpose of this question. Because as soon as you say that, okay, I will, the microservices, they are just producing log lines and I will store them in an Elasticsearch and I will serve all the search requests from this Elasticsearch. Then this question is done. There's nothing else to be discussed. So the interesting aspect is that how do you, if you didn't have any kind of Elasticsearch, how do you design your own? That's the whole purpose of this question. Okay. So that's why we talk about the solution too. Okay. Now, to talk about the solution two, let's make some important observations first. Let's try to understand what Elasticsearch was doing, or how this business of inverted index was being done. Okay. So first important thing is that log messages are immutable. Right? Once you have written them to a log file, you never update them. You only append the log lines. Hmm. Now, what does it mean? It means, so take example of this Shakespeare example, this Shakespeare thing, right? Now Shakespeare's play has been written. Now nobody's updating it, right? So once I make inverted index out of that play, I can just use it again and again and again. Similarly, for our log messages, right? So the log messages which were emitted in previous hour, once I have created an inverted index out of that, I can just keep on using it again and again. I don't need to update that inverted index, right? Okay, so that is an interesting property. We'll see that how does it make a difference. Now, we talked about it in the functional requirements also. We need to store log messages at 3 granularities of latencies. Or maybe you can say only 2 granularities, but bare minimum granularities are there. First is, as a software engineer, you would agree that the log lines in last 4 hours, 8 hours, they are most important, because if you are if any kind of application problem happened or any kind of things are coming, they are generally in the recent hours. Or if you have done any kind of deployment at that time also, you want to monitor the logs in real time for last 1 hour, 2 hour, how your system is behaving, right? So generally, so I have taken this assumption that last 8 hour logs are very important, and they will be queried at a very, very high rate. And this data size is going to be small, right? Small in comparison to the other data, because we have agreed that we will do the retention for 1 year, right? So compared to the 1 year number, this 8 hours is very small. And for this particular use case, latency expectation is going to be small. Latency expectation is going to be low. So I want in real time, almost near real time guarantees. Then tailing would be done on these recent logs only, right? Now this means that all these log lines, when they are converted into inverted index, they need to be stored on some kind of fast storage, right? They should be ideally on memory or SSD at least, right? So this is one use case. Another is medium latency, right? From 8 hours to 7 days. Right? Generally, after 7 days or 10 days, log messages, they are not interesting anymore. There are not practical use cases of accessing logs after that, right? So these kind of inverted index could be stored on a normal disk, normal rotating hard disk, which are cheaper, but they will have higher latency, like 3 to 5 seconds. And then from 7 days to 1 year, all those things, this data size is huge, so we can put them in a cloud storage like AWS S3. Okay. Let me draw a new diagram and explain it better. Okay, so now we are trying to understand that how inverted indexes are being created, how we are serving the low latency requirement, how we are serving the medium or high level latency requirement, right? And how we are powering the search. Okay. Okay. So we saw that there is a queue, right? And there are consumers. and these consumers are actually they are consuming messages from the queue, right? Now, what these consumers are doing, that they read a message from the queue, right? And then they will convert it into inverted index. Okay, so first let's see that what, let's see two or three inverted indexes that we will be creating. There will be multiple inverted index, but let's see two or three inverted index. First could be based on some metadata, right? Let's say on the service name, right? Okay, so let me, yeah. So we have seen this structure of this log message, right? So there is a document ID which has some unique UID. So this is a one. If this is not clear, this is one log message. Like this is which has been converted into a JSON document. So it has a timestamp that at what time it was published, which service it belongs to, the actual log message, that error 403 user ID hacker 123 is not authorized to access order service. This is the actual log line. And it was an error and the environment was prod, right? So one log line is converted into a one JSON document. And when it is converted into a JSON document, a document ID is also added to it. Okay. I'm going very slow here just to ensure that you all are able to understand along with it. Now, okay, so now we have, so for service name, let's say order service. So we will have like, okay, some doc1, doc5, blah, 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 this way. For there will be some another service, right? Let's say user service. For that also maybe some other doc3, doc5, right? This kind of inverted index is being created. This is, let's take the first example of the inverted index. Then there is another inverted index, let's say based on a word, right? Let's say we saw that in this example log, there is a word hacker 123. So we'll say that hacker 123, it appeared in document 5. Okay, so this is how we this consumer, it reads a message, right? So one log line is one message in the queue, and that message is converted into a one JSON document. So this consumer is converting it to a one JSON document, and from that JSON document it's creating multiple inverted indexes, and if that inverted index exists, then it's just appending to it. Okay, please feel free to ask questions if you have any question, if it's confusing you, right? Hmm. Okay. There is a question. Where's the metadata coming from? Is it embedded? I will come to the metadata. We'll come to metadata. So, so now consumer has read a message, converted into a JSON document, and into the inverted index. Okay. Now what we will do is we have two requirements, right? First is the low latency log messages, which are recent, and medium and high latency. Right? So for low latency, so now what this consumer will do, so we will have we'll have search nodes here. Okay. And then it will go and it will update the inverted index on one of the server. So these search nodes is a collection of multiple servers, and it will go and update the inverted index on one of the search node. So how it will identify which search node? So it could be a hash. Right? So it could be a hash. Let me write with a different ink. Okay. So it could be a hash, let's say on the service name, if we are updating for the service name inverted index, mod n. So from this, it will identify that, okay, this is the server, and it will update here. Similarly, for the hacker 123, for this also it will identify and with that which server it should go to, and it will append the inverted index on that particular server. And another important thing is this doc also, right? This document also needs to be stored. Right? So, so on the same server, it will store the document also. Right? So in that case, maybe document 3 here, document 5 here. It will store the document also here. Now, why we are doing this? We are doing this to support the low latency requirement. So, and when we are when we are storing the inverted index, okay. Now I'll check if any question. Yes, there is a question. Yes, it one log line is 10 MB buffer. Yes, whatever. So because that whole buffer has been converted into a one queue message. Yes, thank you for asking that. Good question. Who are the consumers? Okay. What about when one log message is multi-lines? Yeah, in that case, I think Ashish, what happens is that these are we use these separators, special separators here, right? So we have double slash or triple slashes there in those cases, and with that we can take care of this. So this is the part with that comes into the when we are converting the log line into JSON document. Right? So at that time, we read those multiple log lines, the new lines, and we just keep on appending them to a single line with double slash or triple slash n. I hope that answers the question. Okay, moving forward. So yeah, now the next thing that we are doing is, so we have stored it here, and we will also, so this is for the 8 hours, right? 8 hours to 7 days. So for the 8 hours, the data is being put into the memory, and for the 8 hours to 7 days, we are putting them into the disk. Okay. Now for the data older than 7 days, what we, so for that queries, what we are doing is that when we have published, when we have stored the log messages on this search nodes cluster, we also publish the same thing to a queue. So this is a different queue. So Q2, let's say. And this here, like this inverted index information is being published. And from here, it goes to a cloud storage, like S3. So, so, so it goes to this S3. So now whenever any query comes for data older than 7 days, then that will be served from this cloud storage. And data earlier than that, that will be served from this search cluster, the search nodes cluster. Is this cache in memory for 8 hours? Yes, it will. We have it for 8 hours. So we can have a TTL for them for 8 hours, and after 8 hours, they are just invalidated from the cache. Okay, I'm going through this again. Okay, just to ensure that we all are on the same page. So the buffer is okay. There is a question. Yes, Senthil. So they will be stored as flat files in S3 because they are just documents, right? They're simple documents. There's nothing fancy about them. Yeah. So we saw that buffer is emptied and put as a message in the queue, right? And that one message is read, and that one message, as it was pointed out, that it is the whole buffer content. So let's say it's a 10 KB content, yeah, 10 or 10 MB content, right? And then consumer reads them converts them into a JSON document one by one. So for each log line, one JSON document is created. We saw the example of JSON document in one of the slides, that this is how the JSON document looks like. There is a unique document ID is provided, then timestamp, surveys, body, log type, environment, all these things are stored in that JSON document, right? And then for each field in the JSON, right, like service name, environment, right, a different inverted index is created. And in case of body, the actual log message, for each word, an inverted index is created, right? As we saw the example of that Shakespeare. And then we have a cluster of search nodes here. And each inverted index is stored or updated on one of the servers here based on the hash function. Okay. Then that data is kept into the cache for 8 hours to support the low latency requirements, and on disk or SSD for 7 days, right? And the consumer, once it has persisted this data on the search node, it also publishes it to the Q2. From Q2 is inverted index and those documents, they are persisted on a cloud storage like S3, so that high latency requirements for the data older than 7 days, those kind of requests can be served from there. So we are creating, Asim, we are creating different inverted indexes. We are creating separate inverted indexes. So for service name, we have a different inverted index. For environment, we have a different inverted index. Okay, and then ultimately we do scatter and gather, and we find out the matching set. We'll see that. For instance, body, acha, for body, can we have more than one inverted index? Yes, that's what we saw, right? So the inverted index, so each word is a different entry, right? For example, here, so for this body, so the same as the Shakespeare example that we saw, right? For each word, we have an entry in the inverted index. So we are not creating a different inverted index in that case. It's just that there are multiple entries in the inverted index. So for hacker 123, there is an entry. For authorized, there is an entry. It appears as though you are sharding on each of the inverted index, for example. No, we have not talked about sharding right till now, Ito. So right now we just have a logically separate inverted indexes. So one buffer 10 MB will create 1 million doc IDs. Yeah, it can, if that's the calculation coming to. Because these are just log lines, right? Actually, they are just log lines. So you don't have inverted index if you have more than values to unique key field in case of body that have more values. Yeah, for each unique key, we have an inverted index. Yeah. It will be more clear. Just please bear with me. Okay. Just, please bear with me for some time. Even if after that it's not clear, then we will have more discussion. Okay. So yeah. So now what? Yeah. So now if you see, there is a requirement for metadata also here, right? That for which that what is the exact location of the documents in the cloud storage. Right? So there is a requirement for metadata as well. So we call it as the index catalog. So it's actually, let me write here. So index catalog. So like for service name, trace ID, everything. So actually what's happening is that we are storing the actual inverted index on the cold storage, right? In case of this more than 7 days. Okay. So for that we need the metadata. Okay. Actually, now let me go through the actual search, that how the search is powered. Then these things will become even more clear. Okay. Okay. So let's say there is a search aggregator. What its purpose in life is to serve the search queries that are coming from the end user, from the software engineers. Right? So these software engineers, they are sending query, right? That I want to see the log messages matching with my query. So these requests, they come to a search aggregator. Okay. So these a search aggregator is a service, right? And of course, there will be some load balancer here. So the requests are coming to the load balancer actually, and then it goes to search aggregator. Now, search aggregator, it takes the query that has come from the user, and it will parse the query. Okay. And it will identify that the query is for low latency that it is for low and medium latency. So it is for less than 7 days data, or it is for more than 7 days data. Okay. So this is the step one that the query has come, and this is the step number two that we are parsing the query. Query parsing. Okay. So far so good. Now what it does is, in case of low latency, right, it will send the request to the search nodes directly. Okay. And so this query is passed to the search nodes. Right now, remember, search nodes have the inverted index and the actual documents either in the cache or on the disk, right? So when they get this query, so okay, so imagine that this is similar to a Cassandra architecture. Okay, by Cassandra architecture, if you know about it, then you will understand it. Even if you don't, I'll explain it. So let's say it's some kind of ring architecture. Okay, so this is the architecture of search nodes I'm explaining. Search nodes. Okay. So request comes to any one of the server, this query. Right? Now this becomes the orchestrator for that particular request. Okay, and then it will start understanding the query. Okay, the query can be the, let's say the query says, let's keep a very simple query. Let's say the query says that service is order service, environment is prod, and body contains hacker 123. Okay, let's say the simple query is coming. So now this particular server who has become the orchestrator, because it received the request, right? It's not a special orchestrator server, because it just got this request, it became the orchestrator for this particular request. Okay, so in this architecture all servers are equivalent. So now this person, this server, this orchestrator server, it will identify that for each of the field which server actually has the data, right? So again, based on the hash it can identify the server, right? So it identifies that for this service it has to go to, let's say, this server. For environment it has to go to this server. For body it has to go to this server, right? So it will send the request to all those servers. Then these people, these servers, when they receive the request, they will first check in the, so let's say we click on this. So it first checks in the cache. If it's available, if the answer is available in the cache, it will just return from there. If it not, if it is not there, then it checks in disk, right? And then returns the response from there. Okay, so this is the step three. that it parses the query, parse query and scatter. Okay. Then step 4 is this, that all the individual servers are checking in their cache or in the disk, in the disk. Okay, and then they will return the response. Okay, so step 5 is to, so step 3 was scatter, step 5 is gather, right? And in gather step, what the server will do, it will do deduplication, because the documents written can be duplicate, right? And then once it has done the deduplication, it will sort them based generally on the time, or if any custom sorting requirement is given, and then it will the final answer, right? So this is the step 5, and then step 6, that answer is returned. Okay, I'll pause and wait for questions. Is it clear? Okay. Okay, no questions, then I'm happy. Maybe everybody has understood it. Very quickly we'll just revise it again. Okay. Okay, so we are looking at the search use case. Okay, that how the logs are actually being searched, those inverted indexes that we have created, how they are being actually searched. So first step is that software engineer, they send the query. Okay, they send the query, and we looked at the query. That query is very simple, that there is a service which there is a field service that says that, okay, give me all the logs for order service, for environment production, where body contains hacker123. So this search aggregator accepts the request from software engineer and parses it, and it identifies that the query is for less than 7 days data, or it is for more than 7 days data. Okay, so for, let's take this use case that it is for less than 7 days data. So the query goes to the cluster of search nodes. So we saw that this cluster of search nodes is like a ring architecture where each server is equivalent, and they all have different kind of inverted indexes stored into them based on the hash formula. Okay. So the request can randomly go to any one of the node in the search node, and that server assumes the responsibility of orchestrator. Okay. So this is the step 3, that this orchestrator parses the query and identifies that inverted index for service, order service is in which server, the inverted index for environment prod is in which server, for hacker123 it is in which server, and then it sends request to all those servers, it's scattering them. All those search node server, when they receive the request, This is the step 4. They check in their cache first. If it's not in cache, they check in the disk. Check in disk. And they send the response back to the orchestrator. So step 5 is gather, where it will do the deduplication, it will sort them, and it will return the final answer to the search aggregator, and from search aggregator the answer is returned back to the software engineer, the user. The search nodes are three, the three tiered systems: app, cache, and storage. Yes, yes, it was. So if we look at this one server, it's a self-contained server, right? So it's able to serve the request also. It has its storage on the disk itself, and then they maintain cache also. And then actually for cache also we can have another type of cache also. I know that we talked that there is a cache for 8 hours, right? Now there could be another LRU cache as well. So the data which is older than 8 hours but less than 7 days, right, which is on the disk, right? So that data can also be stored on the LRU cache, right? So that data which is being frequently, let's say some bug happened, right, and everybody is interested in a certain type of query. For let's say this hacker 123 turned out to be a black hat hacker, and everybody is looking into their logs, right? So in that case, this LRU cache will be very useful, because all the responses related to this hacker 123 will be stored in the LRU cache for the subsequent requests. So step 1 to 5, what is the ideal response time? So we saw in the requirements that in case when we are serving from the cache, right, for the data less than 8 hours, we are saying that we it will be completed in 400 to 500 milliseconds. Or it could be 1 second also. So generally for logs, we are more tolerant. It's not that it's a very no, it's not an external application in this case, right? So we are okay with some latency. So 500 milliseconds, even 1 second is fine. But I believe since we are having it in memory cache, right, and all this is in the same zone, it's same availability zone, right? So the latencies are going to be uh, very small for individual latencies. So within like let's say if you talk about within a data center, right? Within a data center, if when the different components are talking to each other, it's very fast. It's 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 even less than 1 millisecond also. It's very fast. And when we are accessing the in-memory things, right? Again, they are in single digits of milliseconds. Like 2 to 5 milliseconds is a very fair number to assume. Right? So if you look at the in-memory flow, right, it's going to be very small. It's definitely it can be less than 500 milliseconds in most of the cases, unless we are doing something stupid anyway. And when we are reading from the SSDs or from the disk, right? Now again, it also depends whether we are for the data older than 8 hours and less than 7 days, we have it in SSD or we have it in disk. If it's in SSDs, again, like it will be very fast. Like we can definitely say that it will be 1 to 2 seconds or this. In case of disk, it may go to 5 seconds, 7 seconds. But again, as a software engineer, you also have used logging, right? You have searched through logs, so you know that when you are searching for data older than 7 days on multiple servers, you know that it's okay if it takes 5 seconds or 10 seconds. Hope that answers your question. Okay. Inverted index will only store word to doc ID mapping. Correct. Yes, correct. Search aggregator has to get the complete doc for those fine doc ID. The search aggregator has to send the complete doc back to client. Yes, yes, Ashish. So when, yeah, okay, I missed explaining this in. Okay, thank you for asking. So when, remember we saw here in this diagram. Um, I'm making this square with green again, right? We saw here that we are storing the actual docs also on the server, right? So coming back to this step 1 to 5 that we saw. So these red arrows, right? When they are going back, when each server is individually sending the response back. So they are sending the docs. Yes, it will increase the storage size definitely, but we are taking that hit, right? Because it's only for 7 days. And we have, if we go back to if we go back to the requirements here, the capacity estimation, right? We saw that it's 24 terabyte for 1 year. For 7 days, it's going to be a very small number, right? So that's why we are consciously making that choice that even if I have to duplicate the data on multiple servers, I can do it. Let's see, 20, let's see what the number comes to. 24 TB is for 365 days. So for 7 days, how much it is? Can some of you, can one of you calculate this and put it into the chat box? What this number comes to? Exactly. Yeah. It's coming to zero point 0.5 tera, 460 GB or zero point 0.5 TB, as Ashish mentioned. Right. So it's not going to be a very huge number. We are using disk here. Disk can have huge sizes. So it's a manageable number. Yeah, if this number would have come to 20 TB, 30 TB, 40 TB, and then if we were duplicating it many times, then it would have been a big concern. And again, going back to the functional requirements, we have estimated our numbers to be very liberal, right? Very like 100,000 engineers, 400 billions of lines. We have already taken very big numbers. I hope Ashish it's clear now. It's a very good question. Thank you for asking this. Let me know if you have any more question. Okay. But if there are 10 such nodes and worst case scenario, if all nodes store this, then total will be 5 TB for 7. Yes, so that's fine, right? We already saw in the starting that one server can easily have 2 terabyte to 10 terabyte of disk. So 5 terabyte is still one server. Which step out of this is more expensive? Like if when you are reading from disk, those steps are always expensive. When you are reading in memory, those latencies are very less. And when your requests are going through the data center, the same data center, it's very fast in the data center. So we already discussed that, right? Each of the step is mutually exclusive. Why they will be mutually exclusive? They all are dependent on each other, right? It's like a top down approach, right? First you get the query, then you parse the query, then you identify that it is for less than 7 days or more than 7 days, then you send it to a orchestrator, then orchestrator again parses that query, then it sends to individual servers which have the inverted index and documents, then they send back the response, then you aggregate them, you deduplicate the response, then you ultimately send it back to the software engineer, right? So they are not mutually exclusive, right? What about step 5? Yeah, what about step 5? I mean, what's the question? I'll just take a small loop break. In that time, please, like we'll take a 5 minutes break. So in that time, please go. I'll keep this diagram open here. Okay, please go through this again. If you have any questions, let me know. And please complete the poll if you have not. Okay, I'm back. Step 5. Gather, you deduplicate, you sort them, you return the final answer. I don't believe step 5 is going to be the expensive of all of them, because if you see, it's completely a process which is done on the CPU, right? You are deduplicating them, you're sorting them. Yes, if if there is a poor choice of deduplication or how you're sorting them, then in that case, I believe yes, it could be a slow process. But I don't believe that it's going to be the most expensive one. In this case, the things that look expensive to me are the network transfers, because we are transferring the actual documents, right? And so even though one document is of a very small size, but we are transferring many documents. So that step looks expensive to me. Otherwise, mostly we are doing in-memory operations or we are reading from the SSD disk. So those things look okay to me. Can we not use time series database in this case, as data is time slice and ingestion time and queries are also time slice? But how do you search, Ashish? That is the main point of this question, right? How do you search hacker 123 in all those documents? How do you search for order service in all those log line or log messages? Okay, let's move forward. We still have few slides left, and I believe most of you, for most of you, it would be quite late in the night, right? Please mention on the chat box. Should we move faster here or the pace is fine? I'm just concerned about your about your well-being here. Maybe if you are not waking up, not staying up very late. Okay, Asim says pace is okay. For others, what do you think? Like, should we move faster or it's okay? Nobody is replying. I hope you, except Asim, not other people are not already sleeping. And if you are sleeping, that means my teaching was very boring. So sorry about that. Okay. Okay, I'll assume that things are going fine. It's almost 1 a.m. for me. Can you tell me estimated completion time? Yes, Ashish, I don't know about the estimated completion time because I was thinking that I would be able to complete it in 2 to 3 hours, but there are some questions. So let's do one thing. Now please keep posting your questions. But if your questions are not very relevant to the point being discussed, then we'll park those questions in the end. Okay, and I'll stay. Whoever is interested, then you can stay, and we'll address only those questions which are very relevant to the topic being discussed. Okay, let's move forward. Yeah, so now we come to the another interesting part, that oh, sorry, yeah, what if the query was for more than 7 days data? Okay, so so let's take it on the another page. Okay, so the requirement is for more than 7 days data, right? Now remember few things here. First of all, this the actual data. So by data, I mean the inverted index, and documents are on cloud storage, right? Let's write S3 because everyone understands S3, right? So everything is on S3. So this is the main point, right? That means this data is not readily available. Right? Second thing, we said that we are okay with 5 to 10 seconds kind of latency. If the if the user is it, and this number could even increase more, because if the user is searching for even with lot of data, if that guy says that okay, give me data from March to June, right, for 3 4 months, of course it's going to take time, right? So what do we do? So what happens is that the software engineer sends the query, right? It went to the search aggregator. Search aggregator identified that it is for more than 7 days. Right? It is for more than 7 days, right? So what it did was that it will send a response back to the SE, the software engineer, right? That it's going to be a asynchronous request because I'm going to take time to process your request. Okay, so we can have couple of options here, right? One is that maybe we can have some kind of long polling here, right? or we can have a WebSocket here. So that when the answer is ready, the software engineer gets it. Now aggregator starts processing it. Now in the earlier scenario, aggregator sent it to search nodes. Now let me introduce another layer here. Let's say this aggregator sends request to, let's call it batch search nodes. Okay. So this is a cluster of search nodes which are inherently similar to the other search nodes cluster that we saw, but they'll be behaving in a bit different way. Mhm. So in this case, what will happen is that one of the server gets the request, gets the query. Okay. So it got the query. Okay. Now, remember we talked about the metadata earlier. That metadata comes into the picture now. This is the metadata DB. Now, what metadata DB stores? It stores that, let's say, for order service, what the array of document IDs, right? What document IDs are there, and what's the location of that each of the document ID. So actually, it stores a kind of array. Okay. So first one is document ID and the document URL on the S3 location. So this way it stores this. So what we do is that when the query comes to this orchestrator server, it talks to this metadata DB and tells the DB that give me the all the document IDs and their location. So this database returns that. Okay. Then so now it does the query for order service. It does the query for environment production and also for the hacker 123, right? The same query that we had earlier. So it gets three arrays here, which has the list of all the document IDs and document URLs. From this, this server will aggregate the answer. This is not answer actually. It will just aggregate them. Aggregate them so that main thing is it does deduplication. Once it does the deduplication, and also identifies the intersection, right? Because the intersection is the answer. So the document ID which mentions order service and environment and hacker 123, all of them in them, that is the intersection. That is the part of the answer, right? So once we have got that intersection set, right? Document one, its URL, then let's say document three, its URL. Once it has identified that, then it will make query to the cloud storage, the S3, and it will ask for these URLs that give me these answers, give me these URLs. And once it gets those things from the cloud storage, it stitches them together as one answer and sends it back. Okay. Now there is a scope for improvement also here. Let's say this intersection list comes to be a huge number. It comes to be a very big number, right? So first optimization that we can do is that, of course, the pagination, right? Okay, so the let's say the query said that give me 100 log lines by 100 log lines, right? In that case, pagination will be helpful, and in that case, this is the only improvement. Like another thing is, let's say users page size is more, or the user is expecting all the responses together in some kind of CSV file. In that case, I need to get all the answers back, right? I cannot have the luxury of pagination there. So for those kind of scenario, what we can do is that we can do some parallelization here. So this is the bulk query, right? So we can do the parallelization here. So maybe this orchestrator, since there are multiple servers in the here, so it can spread those queries to multiple servers, and then these all these multiple servers are talking to the cloud storage and downloading data in parallel and sending it back to the aggregator, the orchestrator, and that person is just aggregating all the answers and sending it back. Maybe it's just collecting all the answers, making it a huge CSV file, then compressing it to some gunzip file and putting it into a new location on S3, and then that S3 location is shared with the software engineer, right? Hey, I've got your answer. It's a huge 30 GB file, and I have compressed it and I have stored it on S3. Here is the URL for that. Okay, I hope that makes sense. And another optimization here is that whatever data we have downloaded from the cloud storage, right, we keep it on the disk for some time. So if the similar kind of query comes back to us, so instead of re-downloading those data from the S3 cloud storage, we just have it on our local disk and we return it from there. A kind of caching. Okay, I'll wait for 1 minute if anyone is asking any question. Yeah, we have covered all of these things. This is just theory here. Yeah, let's talk about the sharding aspect. Yeah, so the one thing that we are doing is, which I did not mention earlier, the size of the inverted index. Size of inverted index. So generally what we do is that we let it grow to an acceptable size. So when we are creating the inverted index files, we keep its we keep its size to, let's say, 1 GB. Okay. So when the inverted index file size has become 1 GB, then we create a new inverted index file. So let's say this is index 1. So now we create a new index file, which could be index 2. Right? And then, so this is the sharding that we are doing here. So we are making sure that one file does not become very huge, right? Even before it becomes huge, we cut it down into smaller chunks and save them separately. Right? So whether it's on disk or whether it's on S3, we save it. We save them like this. Okay. Any future growth and sudden spikes. So this is the rehash of the old material which you would have seen in the prerequisites already, right? That we are running at 40% capacity, so we can take care of 2x traffic. If the traffic increases more than 2x, then we can have auto scaling enabled. Then since we have load balancer, so we can always add new servers on the fly. Okay? For storage servers, right? Index metadata and cold storage. Again, the same thing that we are running at 40% capacity and sharding is there. Okay. Now the choosing database or choosing technology or the right tool. So the inverted indexes that we talked about, right? So the Elasticsearch is based on Apache Lucene, and Apache Lucene is the actual programmatic implementation of the inverted index. So, so instead of creating our own inverted index structures, we can use the Apache Lucene library for that. So, so why we would want to do that? So this, okay. So why? Because when we are matching, right? Remember we talked about matching hacker 123. Right? Now let's say software engineer applies some kind of regular expression here, right? So that means we can match hacker 123 also, we can match hacker 245 also, right? So there are multiple matchings are possible. And then once those matching have been done, we have to sort them also. Now this sorting can be done on some other uh, complex requirements also. Okay. Maybe instead of just plainly sorting them on the basis of recency, that means the time, we sort them on the basis of how much they matched. Okay. Let's say hacker 123, hacker 245, these are matching a lot, so they should have higher score. But let's say hack, hackers one, right? So this is also matching the regular expression, but it is matching less. These are matching more. So this should have a lesser score. So for those kind of complex sorting requirements, this Apache Lucene library provides some very good functionality, which we can use just right out of the box. But to be honest, for our, especially for our logging requirement, we wouldn't require these fancy matchings. So even our own implementation should also work fine. Apache Lucene would work, would be required in case, let's say we are matching products, right? Let's say I am searching for Samsung mobile phone. In those cases, there are multiple matchings possible, right? Samsung mobile phone, or I could see for synonyms also Samsung smartphones. Since Samsung smartphone is popular, but Oppo is also popular, so Oppo mobile phone I can also show. So in those cases, there are multiple matching criteria possible. There is a lot of machine learning also applied in those cases. So there, these kind of complex Apache Lucene framework would be very useful. But in this case, it won't be useful that much. Messaging queue we already discussed, like Kafka and these things are there. For the metadata, right? So we can have the wide column NoSQL databases for that. Right? This is like a very obvious choice. And for cold storage, of course, the same S3 and these things can be there. Yeah, these all things are there. Then just let's quickly see that how to identify the bottlenecks in our system. Right? So we identify bottlenecks on basis of the storage throughput, parallelism, hotspot availability, and geo. Right. So for storage, we already discussed, right, that we have shardings and we have the cloud storage and those things. And the data is also not that huge. We have just 24 terabytes. So it's not going to be a big bottleneck. For throughput, again, also this is also a, these are like generally the rehash of the same things that you face in multiple questions. These are like same concepts that can be applied again and again. So if you've seen my previous photo sharing application class, it's similar to that. So for throughput also, we have addressed it. So like we are running our system at 40% capacity, we have auto scaling available, right? So those things will take care of throughput requirements. We have load balancers, we have service discovery, right? I would discuss these things in very detail in the photo sharing application. So if you have not seen that, you can see there. It's a very good discussion that I had. So throughput is also taken care of. Parallelism. So we have two major use cases here. One where we are serving the data less than 7 days and data more than 7 days. So data less than 7 days is a small requirement. There we don't need parallelism. But for data more than 7 days, we already talked about parallelism, right? That is here, that the when we are downloading the inverted index and documents from the cloud storage, we can parallelize that query. We can send it to multiple servers, and they all are in parallel talking to the S3 and downloading from there. Right? So parallelism also we have taken care of. Hotspot. So hotspot generally happens when the same expensive query is run again and again on a particular server, or bombard, or the same query is bombarded on one server, but other servers are relatively free, right? If so, for those cases, again we have caching at multiple places, right? So first of all, we have caching for the 8 hours data. Then second thing is that we have the LRU cache also in this case. Then another caching layer is that when we are downloading from the S3, right? So that data is also we are storing on the disk for some time. Then availability is also the same. Again, like we have auto scaling and we have load balancers and those things. So we are taking care of availability also, right? Geo is not going to be a requirement in this case because the intercontinental latency, right? It is what, 500 milliseconds maximum. So if all my logs are stored in NA, and if software engineers in India are trying to access it, so they will have additional 500 milliseconds of latency. That should be okay for a internal tool. So Senthil, this the columnar databases are also like key values stores only, right? What was your thing? Let me. So since we have completed all these slides, so yeah, let me allow you to speak. Let's now we can have more discussions. Yeah, Senthil, please go ahead. What's your thought process?
Yeah, I mean, can you hear me?
Yes, I can hear you.
Okay. So, I mean, I wasn't thinking about just columnar, but I mean, we are just storing a key value there, right? That's pretty much we are doing in that scenario. So, I
Hmm.
was thinking any type of database, even a regular RDBMS would be okay, right? So, and I understand that NoSQL also will support, white column store will also support that. But I was wondering if there is a specific reason behind picking a white column store.
Yeah. Okay. Not choosing RDBMS should be a no-brainer, right? That why we are not going because we don't need transactions here. We don't
Yeah,
need
we don't have the requirements, so we don't have to. Yeah,
yeah, we don't need complex queries here or
yeah,
complex joins here. We don't need them, right? So RDBMS is already out of scope. Then what choices do we have in NoSQL? So now NoSQL is the choice. In NoSQL, like what choices we have? Like maybe we can have a document-based database like MongoDB.
yeah.
Uh,
That's our case because we don't have a document that's stored. We only have a link. If we store the entire document there, then yeah, I mean, then it makes sense.
Sorry, say it again, please.
Oh, if we stored the entire document just like we stored it in Elasticsearch, then I think
Mhm.
then MongoDB will make sense. But in this case, we are not storing the document, right? We are storing only a link to that document,
Yeah, yeah.
that JSON. So if we have regular NoSQL, I mean, I get it. I mean, in that scenario, it would be,
Mhm.
it could be Cassandra, any other. NoSQL data.
Yeah.
Okay. Or if you want to store it in memory, then it could be a key value store, right? Like Redis or something.
Yeah, uh, Redis we can always have, but Redis is an overkill in this scenario because we are not that latency sensitive in this scenario.
Yeah, makes sense. Yeah. Thanks.
So we are just incurring extra cost when we don't have that requirement.
And how do we also follow up on that? In Elasticsearch, we don't separate the document from the inverted index, right? Because the everything is stored within Elasticsearch. Now, when we move to the greater than 7 days, we are looking at splitting the inverted index and the actual document, copy of the documents. How do we do that, and how does that get split and get sent to S3 and the database for the metadata and things like that? How do we do that?
Okay. Yeah, so we are just maintaining the inverted index and the actual document separately, right? So in inverted index, let's say the hacker 123, right? So so that is, so there we maintain just the, okay, doc 1 has this, doc 3 has this, we maintain that list. So that is a different entity, and then the document 1 is stored separately, then document actual document 3 is stored separately.
Is that stored like in the greater than 7 days section? We store that in a database. The metadata is stored in the database, and then the documents go in S3. How do we
Yes.
store that in the servers for the less than or equal to 7 days section? Because I thought that if you're using Elasticsearch, like Solar,
It's the
then
same,
you just upload it.
similar. Both the approaches are similar. It's just that in the more than 7 days, the things are being stored on cloud on the S3, and they are being downloaded on demand when when the query comes for them. In case of less than 7 days, they are stored locally on the disk and memory, so they are readily available.
Yeah, but on the greater than 7 days, there is a database that has the link for the document ID to the document. Whereas in the less
Mhm.
than 7 days, where is that stored?
So in that case, wherever the inverted index is there, we have the document also. Right? So the inverted index, part of the inverted index is on that server, and the whatever documents are part of that, they are also on that server. So it's readily available on that particular server. So this goes back to the question which Ashish asked, right? So we are duplicating lot of data here, and we said that okay, so our data is not that huge, so we are okay with duplicating. Now let's say if we have this concern that yes, no, the data is becoming very huge and we can't duplicate that. In that case, we again take similar cloud kind of solution here, that let's say my document, oh sorry, what happened, let's say my document 3 is stored once only in this cluster, right? In that case, I bring metadata here also. And then I say that, okay, that document 3 location is on server 1 on this location.
Okay,
But
got it.
still,
So
it is much better because we are not dependent on a external cloud storage. We are still talking in the same service on the disk. So still the latencies are going to be much better.
now I see that because we are using Elasticsearch or Lucene, I mean, or Solar, right? I mean, all are Lucene based. So it just stores everything in the index,
In the server itself, yes.
in the server itself. Yeah. Okay. Thank you.
Okay, thank you, thank you. Thank you for great questions. Okay, coming back to Sneha's question. So we are writing to the buffer. Sneha, is it clear now? Are you there? Oh, okay, she has left, I think. Okay. Asim's question, can you achieve real-time service? Let's take this later once. Any questions related to whatever we have discussed, like how we are storing and how these inverted indexes are being queried? Anything related to that? Okay. Asim has raised hand. Okay. Please go ahead, Asim.
Hi, I had a question like, since we're
Mm-hmm.
talking about the document searches and the inverted
Mm-hmm.
index, I wondering why did you, the MongoDB can be also be a use case, can be used, referenced or no?
For that metadata?
No,
No,
for holding the key value pair, like inverted index itself.
for handling the inverted index itself.
Like, you have keys and values, right? Where
Hmm.
you're creating that like a key value structure, that's a sort of like a document store you
Yeah, so
mentioned.
it's but it's a plain document, right? We do not need anything fancy on it. So we can just store them as a simple flat file on our disk itself. Why do we want another layer of complexity by introducing another database? These are just flat files, right?
Yeah. So, but if the okay, I understand that. So it's mostly like a hash map sort of thing, right? Like key and values.
Yeah,
Yeah.
inverted index is just, it's a hash map.
So I mean, if you have a lot of it, I'm just asking, like, can age-based type of systems can be used where they use morely like to host that key value store and do just lookups, or it is best to do like a server, like the way you are mentioning, like to host the uh, inverted index on the storage itself. I mean, to me, it appeared to me something very similar to how these distributed systems works, right? Basically have regions and serving a specific type of endpoints.
Yeah, I'm afraid I'm not getting a question, Asim.
My question is, like,
Please.
if you have lots of such key value pairs, right? Basically, and your
Yeah,
store is
there are a lot of, obviously, there are millions and billions of key value pairs.
so. I mean, can age based like system can be used like a big table or age based, which are
For
sort of,
storing inverted index.
yes.
So that's what we are saying, right? So inverted index is something which is just a flat file. It's just a key and then value is a lot of comma separated things. So we just need that. We don't need any bells and whistles. Databases come with a lot of extra facilities. We are not interested in any of them,
I see. So in an
right?
interview setting or something, if you sort of mention these type of stacks without a proper justification, then that's probably not a good way. Uh,
Right.
okay.
Right. So as I am also asking you right now, right? Why do you need HBase? Yeah. Do you need any other extra functionality? What what functionality of HBase or what particular feature of HBase would be useful here? Why are you proposing HBase here?
Yeah, I mean,
If
for
you don't,
instance, um, yeah, I mean, the requirement seems to be, um, to probably a better management of if there's any updates coming to those inverted indexes, or then probably it would be much easier to manage through such things. But probably we need to have more specific requirements, right? But maybe you're saying that the requirements are not that strict, so that's why we should just use it, a simple system to host it, pretty much.
Yeah, I'm saying that we do not need lot of functionality here. We just have a flat file, we write to that flat file and we query that flat file. We just so we are not doing any kind of complex queries here. We are not looking for anything, some redundancy or any kind of those things which are provided by databases as extra feature.
Okay, I think I just I think I get my answer. What you're saying?
Sorry, you got the answer?
Yeah, I think I understand. Like
Okay.
I just thought I was just thinking about it, like, and I think the answer which I got is that you just don't use a tech stack until you really see a value why you really want to use it. You know.
Yeah, see,
Simple.
exactly. Let's see if you see this slide. Just a second. If you see this slide, I took almost 5 minutes to explain why we need a queue. Right? I just didn't say that, okay, we'll use a messaging queue and I moved forward. So in an interview also, if you just say, okay, I'll use a messaging queue here, interviewer will stop you and will ask you that why you are using messaging queue here. What are your justifications?
Right.
If you go back to one of my classes, I think it was choosing database class. In
Right.
that, I explained that for the distributed deployment system, you do not need a messaging queue. You can use a RDBMS there.
Right. And I asked you, I think I asked you a very similar question there, and you told me that there's no use case of a queue here or something.
Yeah.
Yeah.
So that's what I
Okay.
said in the starting. So that yes, this is a very good question that you are asking. Please do not shy away from asking these questions because these questions are clarifying your fundamentals. Once your fundamentals are clear, then you can design any kind of abstract system during an interview, even if you have not seen it before.
I was in some of my job roles, and there were some of the companies that I worked, they were using internal searches, and I see that there was a lot of use of age base to host distributed keys, right? Key value stores. So I just thought out of a process, like if you're hosting like a hash type of data structure, maybe the best way to go about is using some type of distributed system that supports the hash lookup kind of
Hmm.
a, that's why my question even clicked there.
Sure, sure. I got it, got it. But yeah, again, you have to know your reasons very clearly.
Just saying that this is just not enough to say, okay, we have a key value store, it's a hash, so we're going to use age base or something. That's right. And what I'm learning, that's not the right approach for the this system design interviews or something.
Yeah, exactly. You see, when you are throwing a specific technology, I have never worked in HBase.
Mm-hmm.
Okay, I don't even know the basics of HBase. I know that it's a columnar database, but now if I'm taking your interview and you tell me, okay, I'm going to use HBase here, then I will, like out of curiosity, I will ask you a lot of questions. Why you're using HBase here?
Understand that. Thank you, sir. Appreciate it.
Asim, is your any other question unanswered? I see there are 4 or 5 questions still there. open questions?
I think
Filler.
I pretty much
Yeah, just
got.
hold on to that. Just hold on. I'll just go one by one. Bhanushri, do you have any question? Bhanushri, just to ensure nobody is missing. Okay. Kanagaraj, any questions, please? Anurag, Ashish. Okay, Anurag is asking a question. Yes, Anurag, please go ahead.
Yeah, hi, the index. Hi, about indexer. Eh, what you're saying is we'll look at the file and search by the key, like the hacker, in a 1 gigabyte file.
Sorry, please say it again.
Like in the indexer is a file you said, and so if I have to search a key in the indexer, it's basically searching a file, long file for the key.
No, it's an inverted index. So for hacker 123, you have an inverted index. So you just you search for hacker 123, and then in the value you see a list of all the documents where hacker 123 appears.
So how do we search for hacker 123 in a long file? So
Yes, so if so in case of if you have it in the memory, then you can search you can store it as a hash map.
so
So
basically
you
it's a
can
local
search.
hash map. You're saying local JVM hash map or whatever your application hash map.
Yes, yes.
Uh, and we are using some kind of LRU cache for the hash
Yeah,
map.
it could be. Yeah, so when we are maintaining it as a cache, like less than 8 hours data, then we have it as a hash map in memory, right? In other scenario, you read it from the disk. Right? When you read it from the disk, then in the application you parse it as an internal hash map, the JVM or like a language specific hash map, right? And then
Also, you
you search it.
uh, also you said you're splitting the indexer, so like my hacker could be in one file and multiple files. I could have the hacker
Hmm.
values or document IDs.
Yes.
So I would be parsing all those files and putting in a hash map, application specific.
Yes, yes. This is a classic scatter and gather scenario. Your queries will go to multiple servers.
I think in the foundation videos it was little different because there I think Omkar was talking about by using document IDs instead of the term.
Mm-hmm.
Like he mentioned term partition and document partition.
Mm.
So here also you're talking something similar, I guess.
We will have so term ID. So actually, you will have to search on a term, right? So term is hacker 123 here.
But that term could be result in stored in multiple servers, right?
Yes, yes.
Because in one server I could have hacker 123 document 123. In another I could have document 345.
Exactly. So I'll explain. See, this is the classic uh, vertical sharding use case. Okay. So this is how your inverted index looks like. Hacker 123, and now you maintain a list of documents here where it's appearing. Document 1, document 2, blah blah blah, document 1 million, blah blah blah, document 10 million, right? It could be millions of documents where it is appearing,
No,
right? Now you see that this this is infinitely growing horizontally.
Yes.
So now that means you will hit a limit. You will hit a file size limit here, right? So when that file size limit hits, you have to divide it into smaller chunks. Let's say document, let's say for storing, let's say one server can store only 1 million document IDs. But here we have 10 million document IDs, right? So that means we are going to divide it into chunks here. So the one chunk where it will store first 1 million entries. Then there is another chunk which stores another 1 million entries. Then there is another chunk which stores another 1
So we are
million.
sharding by document ID, right? Document.
In this case, yes.
Okay.
So, but how we are doing is that we are just limiting it by the size of file. So that's what I said earlier. So the whenever we hit the 1 GB, we say that I'm going to create a new file here. And now all these are going to different servers. This is going on server 1, this is going on server 2, this is going on some server 10. So you see, right? So this is why this is vertical sharding. Right?
It is the same as document sharding, I believe. It is.
What document sharding?
I mean, it is the same. I mean, vertical sharding or document sharding seems the same thing.
What is document sharding?
Document sharding is basically we divide by document, like as you said, like first 1 billion
Ah,
documents
okay.
go to first server.
Yeah. Yeah, so when you are sharding by document ID, in that case, what you are saying is that then you are doing a hash on document ID. You are doing a hash on document ID, and then you are doing modern, right?
Yes.
In this case, I
Yes.
am simplifying it further. I am saying that I am just going to increase the size till 1 GB, and then I will create a new file.
So here, what you're saying, one server will only have hacker ID, or it will have multiple terms. It will only have, in your case.
So it can have multiple files. So it can have a file for hacker 123. It can have a file for production also. It can have a file for some user XYZ. But all the files for hacker 123, they are not on one server. They are here also, they are here also. Similarly, one file for user XYZ is on this server. In this server, maybe another file is on this server.
Okay, I got it. Thanks.
Right? Okay. Thank you,
Can I
Anurag.
ask a question, related one?
Hey, related to this sharding only?
Yes.
Okay, please go ahead.
So remember you were mentioning earlier that you use like you mentioned the example of, let's say there was a body key and there were multiple values, right? Basically, of it. And you said like every value is basically an inverted index. Is that what you were mentioning?
See, there is a file where you have a lot of inverted. So when I said so this is your one big file. Okay. Now you have entry for hacker 123 here, okay, like this. Then you have an entry for in that same line, let's say unauthorized was a word. So unauthorized also you have some entry here. Okay. So, but this is one big file. This is one file.
Okay, so that one key value pair is actually an inverted index. Is that right?
Yes, it is one index.
Okay. But if let's say one key has multiple values, that will also be one inverted index.
This is the one key, right? And these are the multiple values.
Okay, so doesn't matter like how many values can it be, it will still be one inverted index. And based on each key, right? Matters on each key.
Yeah. Inverted index is just a hash map, right? And what is hash map? Hash map is a array of key values. It's right. It's a collection of key values, key value pairs.
So you can always have to search by that key, or you can also go by value, go reverse. Inverted index, wouldn't it, what, like you can, because the value, I mean, it's sort of looks like one key, multiple values. Isn't it look like a parent-child kind of a relationship? Like, you know,
Have you seen system design fundamentals too, Asim?
I have not fully.
Yeah, yeah. So please see that, then you'll have a very clear understanding of inverted index.
Okay.
Mhm. And after that also, if you have any queries, then please let me know.
Sure.
Yes, Ashish, please go ahead.
Hey, thank you for letting me speak. So I have two questions. One thing is on this in file. So it's going to be 5 terabyte file. Let's say you're saying stored wise. Now this is a hash map. So you're going to store this whole in the memory if you have to update one key, but the whole file has to be rewritten back to the storage. So you need that much of memory. Because if you suppose you are storing 7 days of data and hacker rank was in first 2 days, but then it came in seven day again. So you have to dump the whole file back, load the whole file and dump the whole file back after updating the hash map.
You are saying when we are storing it in memory, less than 8 hours data.
On less than 7 days data.
Okay,
So in
okay.
the 7 days you are storing into file, right?
Mhm.
And these are going to be a sequential writes because hash map
Yeah,
is
so
will have a key.
these are going. Yeah, so these are going to be 1 GB files, right?
So even 1 GB file, if you have a hacker underscore this, it will be one key, right? So you have to load all the keys because the one key will not be in multiple files. Otherwise, how are you going to manage the hash map in the memory? You have to load the whole hacker underscore 123 from all the files and files you have into memory. So we'll need that much of whatever the current storage you have size, the same memory you will need it.
Yes. Okay. So you are saying that, okay, so that if the file size is 1 GB and we have to update it, then we are basically bringing that 1 GB file into the RAM, and then we are updating it and then writing it back
Yeah, just
to the
updating
disk.
one key and writing the whole file back to the disk. We can't do a random access and update it.
Yeah.
So this can be a performance hit.
Yeah. Yeah, that's a good point. I honestly, I hadn't thought about it. So let's think what we can do. Maybe maybe we can have it in smaller chunks then, or we can have some kind of
And we
index
have
over
the
this.
and we have a B tree as a value instead of having just
Exactly.
a array list
Yeah,
as the value can have
yeah,
a B plus tree.
true, true. Exactly. I was coming to that only. So similar to a database, we can have a B tree where we identify in the B tree that where that particular node is, and that node points to the exact location on the file storage.
Yeah, and then append that block size, something like that.
Yes, yes, true.
Thank you. The other question I have is the
Awesome,
if
awesome,
I
awesome question.
oh, sure, thank you. The other question I have is this most of the queries which will come from the software engineers going to be a time sliced. So inverted index, I don't think it can support a range scan. It will always be a full scan. Let's suppose I have a timestamp also in my query as a predicate.
Yeah.
So in that case, I have to scan the whole, whatever the inverted index is created for that, I have to scan the whole thing for that just to find out the time range, because inverted index does not support the time range queries.
Yes, yes. Yeah, in that case again, so like Elasticsearch also does this now. So Elasticsearch also provides B-tree indexes for these kind of range queries now. So in that case, yes, we will have this B-tree index for that.
Yeah. So that's the reason I was thinking of if we can put a time series database and the values, we can have the B trees for those columns, whatever the tokens we are, or these words we are indexing.
Okay, you are saying that we can have time series
Because
database. Mm-hmm.
and the values for them we can index it. So because we know the time series, we'll have the handle on those, and then it goes inside that and such if those time series contains those things.
Mm-hmm. Okay. But in that case, I have one doubt. So in that case, wouldn't it happen that all the latest timestamps are going on one server?
Of that you
And that
can
becomes
partition, that you can do a consistent hashing or something.
Hmm.
You need to keep a range, right? Suppose, let's say if it was a numeric value for a metric calculation, you generally know if I'm collecting it 5 seconds and I'm going to aggregate at maximum of 10 minutes or 5 minutes aggregation, then
Mhm.
I can have those in the same server so it does not go across the server. Other than that, it can go. Same thing we can do
Okay.
here also.
Okay. Okay. Honestly, I have not worked on time series in production, never.
No, I
So
also
yes, so my
not worked. I've just read about it. Sorry to cut you.
okay. Okay. Yeah, I've not even read about it a lot. So maybe I'll have to dig deeper into that how it can support. But what you are saying makes sense to me. So.
Thank you.
But again, Ashish, same thing. So if time series database is something you do not have good knowledge, like you have just read about it, you have not worked in production, you do not have good mastery over it, then I'll say that please be cautious before you mention it in
No,
the
no,
interview.
I'm more not the product itself, but the concept from that
Mhm.
database. Instead of, since we are building everything custom here, so
Mhm.
instead of using a product, we can build a custom solution with the same basic concepts.
Mhm. But even for the concept, like if you have a good mastery over the time series, that how it works and how the edge cases are being addressed, then only please mention about it.
Okay, thank you.
Because generally, like RDBMS, MySQL, the key value pair, columnar, document, these are some things like which are the common databases which everyone knows has good mastery over.
Yeah,
So
I've done the
time
time
series.
series more on the metrics calculation and all those where the values are numeric but not ASCII values. So these
Mm,
here, the values are ASCII, not the numeric.
mm, Let's go to Derek, Dheeraj, Maheshwari. Any questions from your side? Okay. If not, we'll go back to Asim. Asim, what was your question?
No, I don't have a question at this point.
Okay. Okay, awesome. In that case, I think we can wrap up for the day. It has been a very long discussion, and I understand that you might have questions about this. So I'm also very excited to discuss more about this in depth. So please feel free to reach out to me on email if you have any questions. And I really loved the discussion. I really loved your questions. There were great questions. So thank you so much and all the best for your preparations.
Thank you, sir. Appreciate it.
Please do not say sir. Raj is fine.
Yeah. Okay. Rajesh.
Raj. Raj.
Raj. Okay, Raj. Thanks.
Thank you. Thank you. Bye bye. Good night.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today